Really nice to meet you. As just introduced, my name is Chaemin Kim from Postec, and I'm really excited to present my work. So this work has done in collaboration with Professor Anna Lee, Jong Ha, and Jung Choi. Before diving into our main topic, I would like to briefly talk about wearable devices. Wearable devices can become an essential tool for monitoring physiology and biochemical information. Many exciting devices can measure heart rate, skin conductance, and step count. More recently, device detecting chemical information such as cortisol, pH, and glucose has also been developed. But for detecting chemical inflammation, invasive method was mainly conducted, which can cause pain. So non-invasive methods have become an active area of research, such as smart contact glass, salvia-based sensor, and sweat patch. But they still have faces some several limitations, like they can cause discomfort, contamination easily, and old new data mixed inside the microchannels. So to overcome this limitation, our research aimed to develop a contamination-free, chamber-specific, and time-resolved sweat collection device by implementing bistable magnetoactive valve that can be individually triggered to switch between open and closed states without continuous power. A key idea behind our system is concept of bistability. In the in a monostable structure as shown in the video on the left, the shape immediately returns to its original state once the external force is removed. However, bistable structure behave very differently. It has two stable energy minima, and when the structure is pushed from one stable state to the other, it can remain in the new configuration even after the wall disappeared. The video on the right shows a familiar example, a push-pop toy. Once you flip the shell with your finger and then release it, the shell stays in the flipped configuration. This simple toy illustrates exactly how the bistable structure holds in shape without any continuous force. So we design our valve using the bistable shell structure shown here. As just mentioned earlier, a bistable system has two local minima. They have two local minima like this. And it meaning it possesses two distinct stable states. In our design, once the shell receives just enough force to transition from the first stable state to the second, it will remain in that new state without any additional energy input. So we just assign these two stable states to the valve operation. First state corresponding to the undeformed shell represent the open state where fluid can pass through. And the second state, where the shell is flipped, represent the closed state of the valve. And by embedding magnetic particle into the shell and applying an external magnetic field, we can trigger the transition between two stable states on the map, just like push-pop we just introduced. This state is maintained unless an external force large enough to cross the energy barrier inside. This allows the valve to reliably stay on open or closed once it switches states. So the valve and device layer are fabricated using soft elastomer-based material. For the magnetic active elastomer, we mix magnetic particle into the elastomer, and by applying magnetization process so that the valve can respond to the external magnetic field. However, some magnetic particles typically reduce optical transparency, which make it difficult to visualize confirming how fluid flows inside the device. So to overcome this issue, we applied a parallel magnetic field during curing, so allowing the magnetic particle to align along to the field direction, just like on the right video. So this alignment significantly induces enhance the material's optical transparency and enable clear visualization of fluid movement. So now we successfully developed a magnetoactive bistable shell structure. However, in the immediate raise a new question: how we exploit its magnetic responsibility in a more active and functional way beyond simply just switching the states. The force applied to the magnetoactive shell becomes from the magnetic torque, and which is given by the cross product of the material's magnetization and the external magnetic flux density. It means that by adjusting the external magnetic field, we can assist the shell in either returning to its original states or remaining in its deformed state. And let's go back to the verb issue. So in the verb terminology, the maximum pressure in the verb can withstand before switching states is called the cracking pressure. Normally, the cracking pressure is fixed once the geometry and material properties of the verb are defined. So the blue dots in this graph can see the resistance times if there are no magnetic external magnetic field. However, in our system, the external magnetic field can support the verb mechanical, either helping it open more easily or keeping it closed. So if the magnetic torque apply in X minus Z direction or in plus Z direction, the valve open more easily, or it can just resist more longer. So this demonstrates that magnetoactive valve, So in this graph, if even the same inlet pressure applied to the valve, some valve can resist longer time, or some valves can open more easily, just changing the external magnetic field. So this demonstrates that magnetoactive valves have strong potential for use in advanced microfluidic system, where adaptive, remotely tunable flow control is highly valuable. So those are some applications for like valve system. And now let me introduce the sweat collection device that incorporate these bistable magnetoactive valves. So first, we have magnetoactive valve layers. This layer contain a total 6 valves, which operating based on the bistable mechanism I explained just before. And valve can freely remain open or can close. And also they have some outlet holes that prevent backward pressure as well as and also they have alignment in to ensure precise with the next layer. Next, we have microfluidic platform layers, and they include inlet hole through which sweat enter the device, and they also have valve chamber that provides space for the shell when the valve is in the closed state. And they also have collection chamber where the sweat is moved. Finally, at the bottom, they have other adhesive layers, allows the device to attach to the skin. Also, because the entire sweat collection device is fabricated from the soft polymers, it is highly flexible and capable of stretching, bending, and twisting without any discomfort. This ensures that device remain comfortable to wear on the skin for extended periods. I have some videos of this is the video how our valves operated. So you can close the valve by indenting, and the valve can be opened by attaching magnets. So when valve is open, sweat can freely enter to the corresponding correction chamber. So As you can see just in the left video, each valve can control independently by indenting magnets. And by controlling each valve independently, we can selectively collect sweat in the desired chamber. So we have 6 chambers. So if we want to just choose the first one, then you can just open it by using magnets. And by indenting the valve, we can collect the liquid on the desired collection chambers. Yeah. So we also tested the device on the skin under real sweating conditions. So the device adheres well and successfully collect sweat in the intended chamber without cross-contaminations. So let's go to the summary. We developed a new type of sweat collection device that integrate magnetic bistable valve for programmable and selective sweat sampling. This platform eliminates cross-contaminations and offering significant potential for next generation wearable devices. I would really like to thanks to my advisors and collaborators for their support. Thank you for your attention.